All right, so remember, how do we find weight again? So very, very much. We are very much today. Here's the food. I'll keep it there. All right, nice. Right, here again, we said mass by gravity and so on, right? Nice analysis. We said, talking about center of gravity and how center of gravity determines stability. All right, the lower the center of gravity, the more stable it is. Something that we didn't talk about is type of equilibrium. So if you look here, right, you'll notice you have three types of equilibrium. You have stable equilibrium, unstable equilibrium, and neutral equilibrium. So basically what it's saying here is that if you displace those objects, they will display, if you displace it, if you apply a force there, they will display either one of those equilibriums. Right? Stable equilibrium, if you look at the first one, if you were to displace it, right, because of the low center of gravity, if you were to move it or apply a force, it will go back to the original point. So that type of equilibrium is called stable equilibrium. Right? When it goes back to the original position, that's called stable equilibrium. That's okay? Look at the next one. If I were to displace this because of the high center of gravity, what will happen to that object? It will topple over. So it will go into a new position, and we call that type of equilibrium unstable. That's okay? Neutral equilibrium means that once it is placed, right, it will go to a new position and look exactly the same. So if I just place this ball, it will be right here in a new position, but in the exact same orientation. So it looks the same. If I just place this, it will fall, probably look like that. That's okay? You understand the difference between neutral and unstable? Neutral, where it goes, it looks exactly the same as how it was. Right? Stable, it will go back to where it was. Unstable, it goes to a totally new position. All right? So you have to understand the difference between the three different types of equilibrium. Right? We talked about this experiment last day. Remember that? To determine center of gravity. All right. So those are some of the things that we had to do. We talked about forces, right? All the different types of forces. Actually, let's just go through all the different types of forces. You have gravity, right? Gravity creates a downward force. You have weight, which is really gravity. Actually, you shouldn't have this here. The force is really called weight, right? But weight is as a result of gravity. So gravity is not really a type of force. It creates the force called weight. Then you have friction, that's a resistive force. You have upthrust. You're gonna put a coal in water. What's happening? Come back up. That upward force is called the upthrust or the coil force. Electrostatic force, you may have experienced this if you take clothes out of the dryer and find the clothes kind of shocking a little bit. That's an electrostatic force. Magnetic force, well, that's between two magnets. A reaction force is if you were to touch the wall and just feel the wall, touch the wall, you should feel it, right? The reason for that is that the wall exerts a force on you. Right? That's called a reaction force. If you stand on the ground, there's a reaction force on the ground on you. Okay? Yeah? Think about it. If you stand on the ground and you feel it, right? So you're feeling it because the ground exerts a force on you. Correct? Right? Those forces are reaction forces. Tension, if you were to pull a rope, the rope has tension. Centripetal force, if something moving in a circle, the force that keeps it in the circle is called a centripetal force. All right? We'll see more of those later on. And nuclear force is like the force in an atom. Right? In an atom, hold it like the protons and neutrons together. their force. All right, so all those are forces that we should have an idea about. We talked about trust and those things. We'll do the celebration later on. Here's an example of M's distance at something called terminal velocity. So if you look here, you'll see that, right? We have this person here, he jumped out of the plane, and as he falls, he has a force called weight acting on him. But as he continues to fall, there's a drag force acting on him. Right? As the speed increases, he has something called drag force. That's the air resistance. Right? And then he'll continue to fall until his drag force and his weight equal. When that happens, there's something called terminal velocity. So as he falls, when the drag upward force equals to the downward force, he'll still fall, but he will fall at constant velocity. That is called terminal velocity. Okay? Right? And then of course, when he turns on the parachute, which one is larger, the drag or the weight? The drag. The drag becomes larger and it goes down equally until he reaches the ground, hopefully it's safely on the ground, right? So those are examples of terminal velocity and what's on those forces, right? We'll talk about force. We'll talk about that a little more later on. Right, for homework, I asked you to read up on levers. Right, just a little quick little note here on levers. A lever is a simple machine. Remember we were doing the little keystone thing? All those were examples of levers. Right, a lever is a simple machine, and machines are designed to make work much easier. Okay. How do they do that? They modify or transmit forces and motion, and they convert different types of energy into mechanical energy. Machines have input and output. For example, here, when you apply a force here, that's the input. And that input force is used to move like this fuse and thing, right? Right? The input force is normally called the effort, and the output is the load. And of course, we have the fulcrum here. So for example, if we had a load here and you apply a force here, that force is called the effort. This is called your load. And in the middle is the pivot. Okay? Everybody take payments for that thing? One pass. And that's going to the notes that I would have read over. Right? We talked about this last day. The greater the distance from the fulcrum, remember the fulcrum pivot. The further away you are from the pivot, the greater is turning force. Remember that? And what is also large? If the turning force is large, what is also large? F. Moment. Right? The moment is also large. Okay. Right? You have three classes of levers. First class is when the fulcrum in the middle. Second class is when the load in the middle. Third class when the effort in the middle. I know the answers here already, but if you look at the diagram, you have examples of first class, second class, third class. The load here, effort here, fulcrum here. First class lever. Enough? Here your fulcrum in the middle, the fulcrum here, your load in the middle, effort on the end, second class lever. Look at that. Look at this. Look at this. Let's go again. Thumb, thumb. Right? Fulcrum here, effort in the middle, load on the end. Right? Remember, you put the effort here, right? To hold the load on the end. That's okay. And last one, fulcrum on the end, load in the middle, effort on the end, second class lever. So based on which one in the middle, you'll figure out the type of lead pointer. Is that okay with that? Right, you have two more here, just make sure you understand, first, second, and third. Right, you also need fishing rod, last lever. Yeah. All right, so that was some of the things I wanted you to look at before we start Hooke slow. All right, so head of Hooke slow. All right, you'll notice everything that we're doing now has to do with forces. All right, so we're going to take a look at what a force is going to do to spring like stuff. All right, so let's take a look at Hooke's law. Right, online something wrong there. Just give me 1 second. Huh? All right, so how many times basically? All right, so let's take a look at Hooke's law here. Right, online, you're seeing the whiteboard.
Yes, sir.
All right, good. Let's take a look at Hooke's law. I want to show you this spring. Hold on, right? Let's show you a quick little. Yeah. So if you look here, right, what you will see here is a demonstration of Hooke's law, right? So we have an elastic material, right? We have an elastic material here, right? We have an elastic material here, and this is the original length, right? You don't want when you keep adding forces for it to be permanently stretched. If it becomes permanently stretched, it will not go back to the original, and then Hooke's law is no longer free, right? So if you look here, we're going to add a weight holder on it. This is applying a force, and you'll recognize that there's an extension. So see that? And then if you keep adding on forces, right? If you keep adding on more forces or more weights, you'll recognize that the extension here will continue to get larger, right? So basically what Hooke going on say is that the more forces we add here, the greater the extension. He said that it's directly related. So the force being applied is directly related to the extension. Okay, if we add a next one again. If we add a next force or next weight here, the extension continues to grow. But Hooke said if you were to exceed the elastic limit, which means that when I take off the mass, take off the weight, it doesn't go back to the original, then that law doesn't apply again. An increase in force will not give you an equivalent increase in extension. Okay, and that's basically Hooke's law. And Hooke's law is applied to all elastic materials. Right? It could be a rubber band or it could be a spring, it could be anything. Right? Or something elastic. Okay with that? Right? So that's basically what Hooke's law is going to suggest, right? That once you increase of course the extension will also increase. So if you have a retort stand and you have a little spring and you keep adding on masses, right? There's an extension here and there's a force that you keep adding there. Hooke said that force is proportional to extension. All right? All right, so this is basically what we go in terms of Hooke's law, right? So make a little sketch and head up Hooke's law. Let me give you a small note on Hooke's law. Right, and I'll show you the calculations that go with it something, right? Because you all know what direct force is. All right, so Hooke's law, right? Oh, yeah, go ahead. Sorry. Let's show you. right here. Hooke's law states that for an elastic medium, Hooke's law states that for an elastic medium, its extension is directly proportional to the applied force on it, provided that its elastic limit is not exceeded. Provided that its elastic limit is not exceeded. Provided that its elastic limit is not exceeded. All right, so there's just something I want to point out here. These two are directly related. Right? We need to understand what directly related means, right? We need to understand directly, right? So if A is directly related to B, is written like that, right? What that means is as A increases, B will increase, or as A decreases, B will also decrease, right? That's what directly related means. And watch this here. This is an expression. So if I want to turn the expression into equation, take off this and write equal K. So this expression becomes this equation, right? This is the equation for directly related. If I said inversely, right? If I said inversely, it means that A is proportional to 1 on B, right? That's the way you write inversely. And
so sorry, more than.
Yeah, more than an increase in A is a drop in B. Or a decrease in A will give you an increase in B. Right? Like for example, it's shown less time on his phone, giving better grades. Right? So they're inversely related. And the formula looks like this: take out proportional and put equal K by 1 on B. Okay, so every time we take this proportional sign off, we put equal on K. Hooke's law. Huh? I'll just show you the answer. All right. Right now, let us set up and say the rule. I think to show you the answer. Actually, take your reading. So, let them mash up all that. Right, so it's important that you understand the difference between those two, right?
So more than how we able to access back some of the live classes?
Just go on the YouTube channel, the name of the school.
Oh, okay.
Go to live and look at the label and the dates. What it is.
Okay, thanks.
All right. So from Hooke's law, force is proportional to extension. It gives you this nice little formula here. Take off that and F is equal to K. So this is the formula for Hooke's law, right? Where K is called the spring constant. Right? K is a constant in all cases there, right? All right, so look here. Let's say we did an experiment. And in the experiment, we add these forces, right? We add 10 newtons and we got an extension of 2 meters, right? How would we be able to figure out now if the force is 25 newtons, what the extension is? Or if the extension is 7, what is the force being applied? How we could figure out X and Y, right? How we could figure out X and Y without actually having to go and do the experiment, right? Yeah. Right, yeah. So we come to this formula, right? Of course, we can only use this formula if what happened here. Anybody remember? We can only use this formula if what? If the elastic limit was not exceeded. You can't use this formula if the elastic limit was exceeded here. So we're going to assume, right? We're going to assume in the experiment, we're going to assume the elastic limit was not exceeded. All right. So we're going to assume that the elastic limit was not exceeded. All right, so good. So first thing first, what do we know? We know, right? We know this is Hooke's law being applied here, and we know that F is equal to KE, right? But we don't know K. And it's done. We don't know K. How do we get K? Substitute some values. There we go. Substitute some values. So we know F is equal to KE, and we know that when F is 10, E is 2. You'll see now there? When F is 10, E is 2. So we can plug it in here. 10 is equal to K by 2. So K is equal to 5. All right. I want to write the SI units here. Put K. Somebody help me out, please. No. Close the door. Anybody else? Meters? Nah, you going far. Kind of walk, you're getting pulled with that. Going out when you wrong. Very close. Newtons? Newton meter per second. K is what? K is F divided by E, right? So if K is F divided by E, F is what? Newtons. Extension is, so it's Newton per meter, right? So it will be Newton per meter, right? Newton meter is for what? Whose SI unit is Newton meter? Moments, right? right? So we just found K. So what do we know? We know F is equal to K, which is 5. Right? Now we can find anything we need. Right? When F is 25, find it. When E is 7, find it. Try that now. Give me a minute. A minute to win it all. Okay. All right, so yeah, try and find X and Y when I'm this. Yeah. I would. All right, so let's see what you got. So when F is 25, you want to find E is X, right? So 5X is 25. So X is 25 on 5, which is 5 meters, right? The SI unit, right? And when F is Y, it's 5 by E. E is 7. So Y is 35 meters. That's okay? Right? Please make a little note that we cannot use this if the elastic limit is exceeded, right? So now we have to have an idea what the graph for this will look like. Right? If you do this experiment and you plot it, right? What will the graph look like? Right? So we're gonna talk about this graph here, right? For all the maths people, you all might recognize that this is a straight line. Correct? It's just a straight line. So Hooke's law on the graph is only obeyed in the straight line part. Right? See this part here? Go to A. That's the straight line part. Then there's a small period, small period where it's still elastic, right? But really and truly beyond that, it's no longer obeys Hooke's law. But it's still elastic. So it will go back to the original side. So there's a point when you can keep adding forces, a little point beyond that, when this will still go back to the original. But if you go beyond that value, this will not go back to the original. It's permanent stretch and you have to buy a new spring. Right? It will not go back to the original. Okay? So once you go beyond that value, this becomes permanently stretched and it's no longer obeys Hooke's law. And the graph is no longer a straight line. It starts to look like this. That's okay? So on the graph, there are three important points. O to A, that's where it obeys Hooke's law. And up to A is where it's proportional. Right? After A, between A and B, it's still elastic. But once you go beyond B, that's it. Right? That is it. It no longer obeys Hooke's law and it's permanently stretched and it will not start back at 2. It will start at some new position. Are you okay with that? And we just see, by the way, if something is not elastic, it behaves as what? If it's not elastic, it behaves like what? Not elastic means what? If you pull something and it's elastic, it goes back, right? But if you pull something and it's not elastic, it doesn't go back. What behaves like that? Huh? Beginning with P. Anybody guess? What? Play-Doh? All right, plastic. Plastic is the answer. Plastic, yeah. Correct, Josiah. Right? So from here to here, we have plastic deformation. All right? Yeah. Play-Doh is not an official definition of that type of deformation. But it can pass. Out of 10, that's about a half. So you get some. Right, catch that graph, I'm gonna give that a note. Yeah. Huh? Now you're looking at book. Oh, for those who are online, in case you're not seeing this, this is O, this is A and B. I have a small curve here, then a curve here, and then we will talk about what happens after C. Anybody can make a guess? What happens after C? If you add a force beyond C, what will happen? It's no good, right? That's it. There. Mash up this way. I'll show you one because that's what they're doing this. Ready? O to A, write it down. O to A, the elastic limit is not exceeded. O to A, the elastic limit is not exceeded. Spring obeys Hooke's law. Spring obeys Hooke's law. Spring obeys Hooke's law. Right? Full stop. The point A is called the proportional limit. The point A is called the proportional limit. Right? The point P is the elastic limit. The point P is the elastic limit, elastic limit. Beyond which plastic deformation begins. Beyond which plastic deformation begins. Beyond which plastic deformation begins. Right? B to C. B to C is where plastic deformation happens. B to C is where plastic deformation happens. And the C is the breaking point. And C is the breaking point. And C is the breaking point. All right, so that is your elimination. That is your graph and how you explain everything with Hooke's law, right? So suppose on the graph, right? I said Kilon. Kilon, take this graph and from the graph find spring constant. What you will do? From this graph, I want some help. I want some help to find spring constant. What would you do? No guess? Alice? A minus B to get the spring constant. So what you do? Read off none. You won't get spring constant. No. Anybody think about how you got spring constant here? Very similar. Similar? If I get long, guess in there. Anybody online have a guess? How would we get from this graph? How we gonna get spring constant? We do have K. Huh? Length of, you get in there, close. Spring constant was what? Spring constant was F over E. Yeah, upside down. Where do you want to say? F by? Yes, ma'am. We gotta make. Anybody have a guess? Online, come online, looking for a guess. I have this graph here and I don't know what to do. I don't know how to get spring constant from it. I've seen these messages. If you call see these messages while I'm teaching, right? Yeah. Nobody ever guess? Look at what we did here. How we can get a value for K. Right? So let's take a point. That's one option. Take a point and find for K. But the better option is this. If you were very good analyst, very good. That's all I'm looking for. It's a graph. So from a graph, you don't want to just take 1 point. You want to take the gradient. If you were to find the gradient of this graph, it's force versus extension. Correct? And what F1E? F1E is K, which is the spring constant. So gradient is spring constant. All right? Gradient is spring constant. It's always important we know what the graph is going to give us. All right? Very good. Let's go again. Copy that down. Right, there is one little question I want to do about the graph paper. Are you have that? How much people have graph paper? All right, there's the next one without the graph paper. Let's see if I can share that. Share it in group first, right? Right, this 2018, I shared in the group first, right? Right, in case it's not loaded, I'll share it here as well. Right, for those who were able to load it, it is number 5 button. All right, start here. Right up. Are we done? So state Hooke's law. Hooke's law is what? Right? Force proportional to extension provided that the elastic limit is plus XT, right? That's the short version, right? Long version, what I gave you. With the aid of a diagram, explain what's the elastic limit. So you will draw that diagram there. Huh? No, A to B is the elastic. Right? So on your diagram, go back to the first diagram. Up till here is the elastic limit. Right? Up to here, nothing beyond P, right? Nothing beyond P is elastic. Anything beyond B is plastic. Right? So this is the elastic limit here. This is the proportional limit here. Okay? So you have to draw this diagram. You okay with us? So the elastic limit is A to B. Anything beyond that, the object undergoes, the object is permanently stretched. All right? Hurry up, draw that fast. Let's take a look at the next part. Adam. Adam. Adam online. Adam. Is there Adam online? No. Hooke, you're online, what you said?
Yes, sir.
Another answer, huh? Alexandria.
You will.
Yeah.
Ansari. Eleven online. Christian here, Diana here, Nuria. What's the name? All right, Nuria, upside down, Malia. Oh, the Vietnamese, sorry. Next one. That's all right, it's in the group. Malia there, Malia, yes, Malia is there, Ashton is here. Theon. Anybody did not hear their name? Kyle online. Josiah, Caleb, Annalie, Alexandria online.
Yes, sir.
Right, yeah. Oh, no, yeah. And your Joy, where is your, I think your name? Sorry, there, Joy. Joy was the last name again? Yeah, Casper now, come close by. Okay. What's up? All right, when I finish this, I'll add it into this next step, right? I think I need to add it. Right, time to possibly bring a little bit. For those who want to know, we are up to that. Right? Today, we will class 2 minutes early. Because we are up. If they are stopped by 5, I will go 5. Right. Try that there. So they give you a spring constant now. They want you to find the weight, elastic limit, not take, they give you everything. Huh. Go ahead. Just one thing you have to remember when you're working it out. I'll tell it. Right, which all came up with to show it. It's your time to shine here. It's some time to shine. Oh, with the right there, boy. So they give you a spring constant, they give you the value there. Calculate the weight of the object. So what are they asking for there? What are they asking for? Okay, they're asking for weight, but in terms of the formula. Force, very good. Right? So they asking you to find force, but the problem is what? Extension is in what? Millimeters. Extension should be at meter. Right? So Narina, sorry. Narina, force is what again? What do you call it? Force? Yeah. That's weight. In terms of spring constant and extension. Force is what? Spring constant by extension. Good. Work it out fast. So it's 2 by 10 to the 2 by 50 by 10 to the minus 3. Right? Those who are online, you can look on the camera, right? I can't write on the screen yet. Right? I can't write here. Yeah. Well, because it's 50 millimeters, right? Force is spring constant by E. Spring constant is 2 by 10 to the 2. Extension is 50 millimeters, so it's 50 by 10 to the minus 2. 10? So that would do that, that would do that, that would do that, that would do that. Correct. 10 Newton. Okay? Pay attention to your units, right? Next part. Oh yeah, easy marks. Online, you all got 10 newtons as well. Right? Remember, you're multiplying 2 by 10 to the 2 by 50 by 10 to the minus 3, right? Okay, so the next part here, let's go together. Right? Everybody pass paper and group, right? Yes, it is here. Right, so they give you the object attached to this frame in B, fell from rest that can be dropped. Alright, that's fine. I think some of you may have got a few. I just give you the formula here. we do not with this school. Right. So scoring and within the right. So you go the order everybody. Yeah. Right. 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 One for Monday or right? Right? So by Wednesday, make sure we have the lab book. I'm at the area meeting. Otherwise, we will have to just select the results and then otherwise do that. I want you to have your lab book, start to write it up one time. Right? Right, sorry. So the last part, I didn't give it, I didn't teach you this yet, but some of you all might know about acceleration. Right, and use B is equal to U plus V. Right, so that's my fault. I didn't show you that again. Right, but those who did it, you could use B is equal to U plus V. All right. So you can skip that part out. Let's take it, right? So let's just run back to the node. There's the next question we have to do, but you have to actually draw the graph, right? Right? Yeah, all right. So we just completed Hooke's law. We talked about how to find all these little things, right? All right. By the way, this graph looks like this because they plotted extension versus force. So it curve in the other direction. Let's see now there, Anya. Okay, now. Curve in the opposite direction, right? The graph I have on the board is force versus extension. Okay, so let's make sure you know in case they ask you which one, what the shape will look like. Right? Let's just run through some quick definitions and we finish, right? So density, right? You all may have put the term already. Density is what? Mass per unit volume, right? How much mass you have in every meter cube. All right. So your density is mass per unit volume. If you look here, you have the same volume in A and B, right? But which has the larger mass later, A or B? A. So which will have the larger density? A. Mass per unit volume. So the more mass you have, the greater the density. Right? So if you look at cube A and cube B, cube A is more dense than cube B. All right. However, cube A is considered denser because it has more mass. Cube A has twice as much mass in a cube B. Therefore, we say that cube A is twice as dense as cube B can be made denser by adding more mass or decreasing the volume, right? Okay. Quickly, this is the formula for density, mass on volume. The symbol is that funny looking little P there. Right? It looks like this. And it's called rho. It's called rho. Right? And as I said, it's mass on volume. For those who have trouble making subject formula, which you should. Right? You can learn this little triangle. If you want to find mass, fraction of mass, you'll get density by volume. If you want to find density, fraction of density, you'll get mass over volume. Right? SI unit, very important. kgm and Q. All right. If you want to find the density of an object, you need to get its mass and its volume. Anybody remember in Form 1 how to get the density, how to get the volume of an irregularly shaped object? If you have a rock, how you accurately get its volume? From Form 1. Huh? Use a measuring. Use a measuring cylinder, put the rock in the measuring cylinder and look at the difference in volume or what? Something nice now. Can go Form 1 just the other day. I was just the other day. Right, so you can use the volume method with the measuring cylinder, or you can use this thing of it, or you don't have it. You can use this here on the displacement can. Pull in water, throw the rock in, and the volume will fall out. Remember that? Right, but there's a next option. You can use the measuring cylinder or you can use the displacement can. Okay. All right, so no major calculation. Just one thing we have to know is something called relative density. Right? Relative density is a given ratio of the density of the substance to the density of a next substance. So if I ask for the relative density of substance A over substance B, it has divided. Anybody remember what the substance that always be underneath here? In relative density, there's a substance that we always use to compare everything else with. What? Amen. Or remember something. Right? And anybody remember the SI unit for relative density? Do you remember it? Very good. But we have none. Right? Very good, Nathan. Nathan said no because we don't have one. All right? Very good. So your homework will be continuing to read on, right? Going on to kinematics. So for homework, read up on kinematics. Right? All right, online. You have to log out, right? Online, you have to log out. Those who have labs, those who do in lab, make sure and come out next week, right? All right, you have to log out. Bye.